Last episode, we measured superheat on the low side and proved the compressor was safe. Now we cross to the high side of the system and measure its mirror image. Subcooling. The good news is the procedure is almost identical, just on a different line, so this is going to feel familiar fast. Quick reminder of what subcooling is. It is the number of degrees that the liquid refrigerant has dropped below its saturation temperature. We read it on the high side on the liquid line, and its whole job is to prove the charge. It is your single best read on how much refrigerant is actually in the system. The roadmap is the same 5 moves you already know. 1. Stabilize and check the air side. 2. Read the liquid pressure on the high side. 3. Clamp a thermometer on the liquid line. 4. Convert that pressure to a saturation temperature on the PT chart.
5. Subtract.
Same dance, high side. Let us go. Everything you learned about earning the reading still applies. Let the system run a solid 10 to 15 minutes so the high side pressure settles. Verify your airflow first, because a starved coil throws the whole system off, high side included. None of that changes. What changes is which pipe you reach for. For superheat, you found the big, cold, insulated suction line. For subcooling, you want the opposite pipe. The liquid line is the smaller diameter line. It is warm to the touch, sometimes hot, because it is carrying high-pressure liquid that just came off the condenser. And it is bare copper, with no foam insulation on it. So before you clamp anything, put your hand on both lines. The fat, cold one wrapped in black foam is the suction line. Leave it alone this time. The skinny, warm, bare one is the liquid line. That is your subcooling line. Big, cold, insulated with superheat. Small, warm, bare is subcooling. Move 1. The pressure on the high side this time. Attach your high side hose to the liquid line service port and note the pressure. That is a big number compared to the suction side, because this is the high-pressure liquid leaving the condenser. Move 2. The temperature. Clamp your pipe clamp thermometer, or your insulated probe, onto that bare liquid line, on a clean section of copper, close to where it leaves the outdoor unit. And yes, the same insulation rule applies. Even though the liquid line is bare, you still wrap foam or putty over your sensor, so the outdoor breeze is not stealing heat off your probe and faking a low reading. The mistake here is the reverse of last time. Now the danger is clamping the big insulated suction line by habit. Do not let muscle memory put you on the wrong pipe. High side hose on the liquid port, thermometer on the bare liquid line, sensor insulated. Then we do the arithmetic. Same conversion as before, just with the high side pressure. You have a liquid line pressure on the gauge. Take it to the pressure temperature chart for our 410A. On a 410, a system, a liquid pressure of about 435 psig converts to a saturation temperature of 115 degrees. So 435 on the gauge becomes 115 degrees on the chart. That 115 is the temperature the refrigerant condenses at that high side pressure. One quick honest note for the students following along with the written guide. The guide rounds that pressure to about 418. When we checked it against a precise 410A chart, a true 115 degree saturation lands closer to 435, so that is the number we are using. The lesson is the lesson either way. Pressure in, saturation, temperature out. Same digital manifold, same paper chart, same move as the low side. Hold on to that 115. Last move, the subtraction, and notice it flips direction from superheat. Go back to the thermometer on the liquid line and read the actual line temperature. Say it reads 105 degrees. Subcooling is the saturation temperature minus the liquid line temperature. 115 minus 105 is 10. You have 10 degrees of subcooling. Watch that order. For superheat, we did line minus saturation. For subcooling, we do saturation minus line. The bigger number is always on the left, so your answer comes out positive. Now read what it means. On most residential systems with a TXV, A healthy subcooling window runs about 8 to 14 degrees, and the equipment data plate will give you the exact target. Our 10 degrees is right in the healthy band. Here is what the number is telling you. Low subcooling means barely any liquid is stacked up in the condenser, which points toward an undercharge. High subcooling means liquid is backing up and flooding the condenser, which points toward an overcharge. 10 degrees says the charge is right where it should be. There is one rule that comes straight out of subcooling, and it is tested and it is field critical, so do not miss it. How you charge a system depends on its metering device. If the system has a thermostatic expansion valve, a TXV, you charge it by subcooling. You add or recover refrigerant until the subcooling matches the target on the data plate, usually somewhere around 8 to 12 degrees, and then you verify that superheat landed in a sane window. You never charge a TXV system by superheat alone because the valve actively controls superheat, so superheat barely moves while you add refrigerant. It will lie to you. The other case, if the system has a fixed orifice, a piston, then you flip it around. You charge to a target superheat using the wet bulb chart for the current conditions, and the subcooling just falls out wherever the math lands. So tie it together. TXV, charged by subcooling. Fixed orifice, charged by superheat. Match your method to the metering device every time. Lock in the 3 from this episode.
1.
Subcooling lives on the liquid line, the small warm bare line on the high side. Get on the right pipe.
2.
The calculation flips from superheat. Subcooling is saturation temperature minus liquid line temperature, and on our example, that was 115 minus 105 equals 10 degrees. 3. Subcooling proves the charge. Low points to undercharge, high points to overcharge, and on a TXV system it is the number you charge by. In the next and final episode, we put both numbers on the table at once and read the 2 gauge signatures that tell you exactly what is wrong with the system. I will see you there.